In today's lesson, we're going to talk about rate of change. So we're going to continue to talk about rate of change, but look at unit rate of change and average rate of change. So we're going to just extend what we've been doing a little bit further and introduce a new concept that will allow us to look at the average rate of change for nonlinear functions. So let's go ahead and recall what rate of change is. Rate of change for a linear function is just the slope of the graph of the line, let's say. If I'm looking at unit rate of change of a linear function is the amount of change that occurs in the output per unit change of the input. So when our change of x is equal to 1. So let's say we want to convert any rate of change to a unit rate of change. Well, why would we want to do this? Well, normally when you're talking about rate of change, for example, the speed limit, you always talk about miles per hour. You don't say I drive 120 miles per 3 hours. No, you reduce it to a unit rate of change. 40 miles per hour is the speed limit. So let's say in this first example, Millie walks 6 miles in 2 hours. If Millie's rate of travel stays the same, constant rate of change, how many miles can she walk in 8 hours? Well, the first thing you're going to want to do is set up a ratio. And we have to be careful of the units. Now, a ratio would be 6 miles for every 2 hours. So that is the original ratio that represents the rate of change. But what if I want to talk about a unit rate of change? I have to revise this, simplify this fraction so that I can actually look at a unit, a change of x to be 1. So if I simplify, divide this by 2, I'm going to get 1. Divide this by 2, I'm going to get 3. So our unit rate of change would be 3 miles for every 1 hour. So 3 miles per hour. Now, we have to think about how we can multiply our units. So remember, we want to answer a specific question. The question was, how many miles can she walk in 8 hours? So this is where we have to multiply our rates because we don't want to know how many she walks in 1 hour. We want to know how many miles she can walk in 8 hours. So I'm going to take that 3 miles per hour, per 1 hour, and I'm going to multiply both the numerator and the denominator by 8 miles per 1 hour. And that is going to give me 24 miles for every 8 hours. So if you notice, each of these fractions are equivalent. So this 24 over 8 is equivalent to 3 over 1, which was equivalent to 6 over 2. So, of course, these should all be equivalent. Now, if I wanted to graph this information, I could say, all right, well, if my time, well, think about what's my input and what's my output. Miles per hour, for every hour, I'm going to go a certain number of miles. So if I don't travel any hours, well, I've traveled no miles. We said for 1 hour, we travel 3 miles. For 2 hours, we traveled 6 miles. And I could just continue on, since I have a constant rate of change, adding 3, right? And this would be for 3 hours, 9 miles. We should see that our change of y is 3 and our change of x is 1. So a constant first finite difference means I have a linear function. And I know, I didn't like counting by ones. So that's 0, 0, 1, 3, 2, 1, 2, 3, 4, 5, 6, and so on. Now, obviously we're driving, so we're not just driving an hour and then driving, we have all the time in between. So we have, if we were to extend this, a linear function. Now, we know our independent variable is hours, so we're really only looking at this first quadrant because time can't be negative. Distance can't be negative, so I'm kind of confined to this first quadrant. Now, let's say you're given this table of values. Given this table of values, what if we want to try to determine the relationship? Well, first of all, let's check to see if this relation is a function. So I'm scanning my x values, my domain values, and I see that none of them are repeated. So if I don't have any repeated x values, I definitely don't have to worry about those different same x values going to different y values. So is it a function? Yes. So now we have to determine if it's linear. So I can go ahead and rewrite this table if I wanted to in ascending order with respect to x, and then I could look for a constant first finite difference. Well, this is going to be linear. We do have a constant first finite difference, and it doesn't matter which set of ordered pairs we're looking at. I'm going to get a constant first finite difference. So our change of y is 12 over our change of x. So 12 over 6 reduces to 2 over 1, or just 2. But this is my slope. So if I'm looking at a unit rate of change, I do want to look at the ratio, the fraction for when the denominator is 0. So let's say I want to write the rule in slope-intercept form. That's going to be y equals mx plus b. I've calculated my slope to be 2. And the question is, what is that b value? But if we remember, the b value is just the y value of the y-intercept. The y-intercept is when our x value is 0. So to identify the b, all I have to do is look at the y value that corresponds to the x being 0. So that is 1. So the equation that represents this linear function is y equals 2x plus 1. So again, slope is defined as the ratio of the constant change in y to a corresponding constant change in x. So it describes how fast our y is changing with respect to our x changing. The rate of change is the slope of the line. Now, what happens if our function is not a straight line? So the function is not a straight line. So if I look at that, I see I have a function, but it is not a straight line. Well, what we can define is an average rate of change, an average rate of change. And to calculate an average rate of change, it's exactly what you think it would be. I would have to pick 2 points. So let's say I've been given this point and this point. So I have our corresponding data points. I can draw a line passing through those 2 points. The line passing through those 2 points is known as the secant line. So the line passing through the 2 points is the secant line. So here is my secant line. That line, that secant line, has a slope. The line passes through these 2 points, so all I would have to do is calculate the slope of that line, pick a point, substitute back into the equation to write the actual equation. So again, if you have a nonlinear function, a function that is not a straight line, you can calculate what's known as the average rate of change just by picking 2 points on the line, drawing a secant line passing through those 2 points, and finding the slope of that line. That is your average rate of change. So let's go into a little bit more detail about this average rate of change. Again, the average rate of change has to deal with a nonlinear function, let's call it f, on an interval. So here is an interval. We're including the endpoints. And it is the slope of the secant line between those 2 points. So here I've been given 2 points, P1, P2. It has a corresponding x1, y1 value for point 1, and an x sub 2, y sub 2 value for point 2. Now, M represents slope. I have a little subscript SEC to say I'm calculating the slope of the secant line. To find the slope of the secant line, well, remember, slope is change of y over change of x. Okay? So if I'm looking at my change of y values, it's the function evaluated at the second point minus the function evaluated at the first point. So that's my y2 minus y1. I'm just using function notation. And that's over x2 minus x1, which we are now going to call h. H is what's known as your step length. Okay, now that may be a little bit confusing, but we're going to draw a picture to make sure that we really understand what we're talking about with this notation. So this right here is what is known as the difference quotient. This is the difference quotient. Change of y over some step length, which represents our change of x. So h is just the change in x. I don't know if you can, that's kind of ugly, so let me try that again. H is just the change of x. So let's draw a picture to make sure we understand what we're dealing with. So we have an independent variable x, a dependent variable y. I'm going to begin by looking at a nonlinear function. So here is a nice nonlinear function. Now, on that function, I want to calculate the difference quotient, the average rate of change. So that means I need to look at 2 points. So let's look at point A. Let's take a little step h, and that's going to give me to the point A plus h. I can also call this x1, take a distance, and say this is x1 plus h. x1 plus xh is x2. So I'm just saying I have 2 points, and there's many different ways I can write it. This distance is h, so I can either call this A and A plus h, or I can call this x1 and x1 plus h, or even x1 and x2. Doesn't matter. They all mean the same thing. Now, there's going to be 2 corresponding points on the function, on the graph of the nonlinear function, and let's say they're those 2 points. So let's look at those points. They have, and those are kind of ugly points. I should have drawn my graph a little different, but this will still be able to do it. It just isn't as obvious. So here I have a point. That point is going to be A and the function evaluated at A. Or I could call it x sub 1 and the function evaluated at x sub 1. So its height is the function evaluated at x1. or the function evaluated at A. And I want you to get comfortable with this notation because it doesn't really matter what I'm calling the input value. This is just a function, f of x, and I'm evaluating the function at 2 points. This other point is the function evaluated at the second point, or the function evaluated at x sub 1 plus h, or the function evaluated at x2. All those things mean the same thing. Now, if I come over here, this is the second y value, the function evaluated at x2, or the function evaluated at a plus h. It doesn't matter how you write it. Now, what am I looking for? I'm looking for the slope of this secant line. How do I calculate the slope of the secant line? Change of y over change of x. It's just the slope. The difference quotient is just the slope of the secant line. We just have fancy way of writing it. So again, average rate of change of y over change of x, f of a plus h minus f of a all over our step length h. That's just change of y over change of x. So again, I'm going to say it 5,000 times. The difference quotient, the average rate of change, is just this. It's just slope of the secant line. So let's say I give you a function. Here's my function. And I'm asking you to find the average rate of change on this interval. So this is the interval I'm looking for. So to find the average rate of change, all I have to do is evaluate the function at the first point, evaluate the function at the second point. Okay, so that would be f of -2 and f of -3. And then I'm just substituting into this function the different values of x. So -2 times -2 squared plus 1. And -2 times -3 squared plus 1. Well, -2 squared is 4. 4 times -2 is -8. -8 plus 1 is -7. If I'm looking at the second point, the second x value, -3 squared is 9. 9 times -2 is -18. -18 plus 1 is -17. So I have 2 points. I have the input -2 with the corresponding output -7. And I have the input -3 with the corresponding output -17. So this is point 1. This is point 2. I'm just substituting into the difference quotient, into the slope formula. So then I have change of y over change of x. So that's -17 plus 7 over -3 plus 2, which is just -10 over -1, which is just 10. So the difference quotient, difference quotient, the average rate of change of the slope of the secant line passing through these 2 points on this nonlinear function, the difference quotient is 10. Okay, what if I give you this function and I say find the difference quotient? Well, but I didn't give you any endpoints. So I want the difference quotient, an expression that I can use given any 2 points. So the difference quotient of this function. Okay, well, I know what f of x is, so I need to figure out what f of x plus 1 is. or x plus h, sorry. It just means everywhere I see an x, I'm going to substitute x plus h, and then you know you have to distribute. So f of x plus h is 6x plus 6h plus 1. And then what was the difference quotient? It was change of y, the function evaluated at the second point minus the function evaluated at the first point, over h. And that's any h. And where is that h coming from? That h is just x plus h minus x. Well, these cancel each other out. That's where the h comes from, right? Okay, so I know what f of x plus h is. F of x plus h is this. So I can substitute in f of x plus h as 6x plus 6h plus 1. And I'm going to subtract my original f of x. My original f of x was this. So that is 6x plus 1. That's over h. Now, I know I have to distribute. So that is going to give me 6x plus 6h plus 1 minus 6x minus 6 all over h. And then these are opposites. And then I can combine these. And so what do I get? I get 6h. Well, that's not a 6. That's a 1. Shame on me. Nobody said anything because nobody's here with me. Negative 1. Okay, so there we go. These are opposites. These are opposites. I know this is still over h, so this is 6h over h, and look at that. So my average rate of change, my difference quotient is 6. Well, what kind of function was this? Linear. So it's a line. So what is the difference quotient? Just the slope of this line. So we just proved it. That's fantastic. All right. What if I give you this function I asked for the difference quotient? Well, the first thing I have to do is figure out what f of x plus h is. Substitute in x plus h everywhere I see an x. That's a binomial squared. So I have to FOIL. So that's my f of x plus h. And to find the difference quotient, all I need is f of x plus h minus f of x all over h. So f of x plus h is x squared plus 2xh plus h squared. That's going to be minus x squared all over h. Okay, so now let's see what we have. Oh, these are opposites. So that's just going to give me 2xh plus h over h. Now the question is, can I simplify that anymore? I sure can. I can simplify the h with each of these. So that just gives me 2x plus what? H. So this is our difference quotient. Now remember, that numerator was a binomial, so when you simplify, that h has to go into each of those terms. Now, let's talk about how we can identify intervals for which a function is increasing decreasing, or constant. So those are math terms. So if I want to talk about when a function is increasing, a function is increasing, the function is increasing when the slope is rising, greater than 0. And right now we're only talking about linear functions. You know, there's a little bit more to it when the function's nonlinear, but I'm talking about linear functions. We say that the linear function is increasing on the open interval, negative infinity to positive infinity if the slope is greater than 0. So that means it's going up. We say a function is decreasing, again on an open interval, if the slope of the line is less than 0, negative slope. Makes sense. And we say that the function is constant, again on this open interval, negative infinity to infinity, if the slope of the line is 0. So what type of line is that? A horizontal line. We say that the function that has a slope that is undefined, if the slope is undefined, then what type of function is it? Well, it's not a function. Why? Because it's just a vertical line, right? Vertical lines have undefined slope, infinite slope. So let's look at the definition of what it means for a function to be increasing. We always define a function to be increasing, decreasing, or constant on an open interval I. It must be always defined on an open interval. The function is said to be increasing on an open interval if f of x1 is less than f of x2 whenever x1 is less than x2 for any x1 and x2 in the open interval. So notice, these are our y values. These are our x values. So what does that mean visually? Well, if I'm looking at a function that is increasing, we said that x1 is less than x2. x1 is less than x2. What else do we know? F of x1 is less than f of x2. So that means this point has to be less than this point. Is that not increasing? Yes, it is. Right? Because this point here is x1, f of x1. This point is x2, f of x2. And again, we're talking about an interval that is open. So that's open interval. So if I were to ask you to sketch the graph of a function that is increasing on this interval, well, then that means 1, 2, 3, negative 3 to 1, 2, 3, 4. From here to here, on this interval, it has to be increasing. Now, you may say, oh, I have, closed, open. It's always defined on an open interval. So it doesn't really matter what's happening outside of that interval, but in this interval, it has to be increasing because that's what we're talking about. So that would be an example. A function to be Now, let's talk about what it means for increasing. For a function to be decreasing on an open interval, again, it's always defined in an open interval. What it means for a function to be decreasing, that means it's going down left to right, then for any, let's say, x1 that is less than x2, where x1 and x2 are in that open interval, f of x1 has to be greater than f of x2. Again, let's see visually what we're talking about. Well, I have an x1 that is less than x2, and I have an f of x2 that is larger, f of x1 that is larger than f of x2 right here. So that means from here to here, it is decreasing on that open interval. So if I ask you to sketch a graph of a function that is decreasing on the interval -3 to 4, so here's my interval, -3 to 4, for it to be decreasing, well, that's an example, and it doesn't matter what's happening here, right? It only matters in that interval. Now, what does it mean for a function to be constant? Again, defined on an open interval. Well, that just is telling you that the function evaluated at the first point has to be the same as the function evaluated at the second point. And what does that mean? Our y values are equal. So if I want to graph a function that is constant on this interval, here's my interval. For it to be constant on this, well, that's an example in itself. There's constant, right? The change of y doesn't change. I mean, our function y values don't change. Now, what if I put together? What if I said, okay, let's graph a function that is increasing on this interval, decreasing on this interval, constant on this interval, and decreasing on that interval. Well, the first thing I'd want to do is maybe look at these intervals. So from -infinity to -1, that's my first interval. It has to be increasing on that interval. Then it has to be decreasing from -1 to 1. And then it has to be constant from 1 to 3. And then it has to be decreasing from 3 to infinity. So let's look at that. This is increasing on this interval, decreasing on that interval, constant on this interval, and decreasing on that interval. That's an example. Do we see those different intervals? Now, within this, some other terms that we have to be familiar with are relative maxima and relative minima. Max and min. A function value, let's say f of a, is a relative maximum, also known as a local maximum, not global. Relative or local maximum, relative max, local max, if there exists an open interval containing that x value, that a value, such that the function evaluated at that point is always larger, more max, let's say, than any other x's in that interval. So let's talk about that. Let's say we have a relative max of y equals 3 when x equals 2 on the interval 2 to 3. So from 2 to 3, or no, sorry, on the point 2 to 3. My apologies. On the point 2 to 3. So x is 2, y is 3. We have a max of 3 when x equals 2. So this is the point. Then anywhere else has to be lower. that is the max. And I can define it on this interval here. I'm just saying there exists an interval, a little neighborhood around this point where there is no point higher, no y value larger than this point. Similarly, I can ask you to sketch a graph that has a local max at this point on this interval. So on this interval, so here's the interval that I'm looking at. I'm saying there exists a local max at this point on this interval. So in this interval, I can't be any higher than that point. Outside that interval, it doesn't matter. But in this interval, I cannot be any larger than that point. Now, there's also something called a relative minimum, relative min, local min. It's saying if there exists, again, an open interval containing an x such that the function evaluated at that point is less than any other point on the interval. So for example, I'm saying a function has a local minimum at the point 1, 3. So that's my lowest point, my local minimum on this interval. Here's my interval. This has to be the lowest point. Anything else doesn't matter. So local max, relative max is the highest point in an open interval. Local min, relative min, is the lowest point in an open interval.